Assalamualaikum warahmatullahi wabarakatuh. Okay, my name is Muhammad Ariff Imran bin HASSAN. Today I want to present about my PSM. The topic that I choose is study on impact of various nanofluid on heat exchanger cooling performance. Okay, firstly we go to content. I have introduction, problem statement, objective of study, visitor review, methodology, research and discussion, and lastly for conclusion. Okay, we go to introduction. Many systems nowadays use this technology such as microprocessing, electric vehicle, and aerospace application. One of the main way to adjust the heat transfer in small component is to apply micro channel heatsink, which improve the heat transfer process via extending heat transfer interface. Nanofluid is the fluid that contain size particle. It called nanoparticles. Nanofluid can be classified into four categories. First one is metal base, second one is metal oxide base, third one is carbon base, and lastly is hybrid mixed metal base. Nanoparticles have an intrasurface area which allow to increase heat transfer. Next we go number 2 is problem statement. Since the macro channel heatsink develop continue to advance, it allow the electronic device to work more efficiently and long time. Nowadays, by using air cooler method, cannot deliver the best performance and cannot work for a long time. Many systems in this world avoid to use water cool or nanofluid because afraid leak in the system and only make the higher cost to the repair. Third one is my objective of study to study on impact of various nanotype on heat exchanger cooling performance. Number 2 is to determine the impact of various nanofluid by using simulation on heat exchanger cooling performance. Lastly is to analyze the effect of flow characteristic which various type of nanofluid. Number 4 is my literature review. The first research is the topic is experimental study to obtain the viscosity CO2 loaded nanofluid, effect of nanoparticle mass fraction, temperature, base fluid type to develop correlation. It conclude that the effect of temperature and base fluid type is more significant on relative dynamic viscosity at C2O nanoparticle mass fraction higher than 0.1 concentration. The second research is investigate into the effect of slip boundary condition on nanofluid flow in a double layer microchannel. The research examined the laminar flow and the heat transmission in double layer microchannel which constitute top layer in this work. The primary objective of this study is to cool the micro heat sink, analyze the condensate. The third one is experimental investigation of C2O water nanofluid flow and heat transfer inside a microchannel heatsink. By using C2O water 4.5% concentration, nanofluid give the worst result for temperature, heat transfer coefficient and energy performance coefficient, and the result is by using 1.03 concentration. Lastly, for the investigation of MHD effect of nanofluid heat transfer in microchannel. The impact of magnetic field intensity, wall, hypermobility level, and nanoparticle volume fraction on flow hydrodynamic and heat transmission are through investigate. Okay, number 5 is my methodology. First one, we go to material selection. Next, modeling, meshing, and CFD. CFD meaning is computational fluid dynamics. And lastly, we go to comparison. Okay, for the material section of micro channel heatsink, I use aluminium. Okay, in ANSYS software, only three type to choose, which is thermal conductivity 3234, density 2.07, and specific heat capacity 897. Next, we go to material section for base fluid and nanofluid. For this simulation, I use TiO2 water and ZNO water, which in zinc, nanofluid zinc and nanofluid titanium. Then we go to modeling. Okay, the model will be sketched and extruded to make 3D model by using SolidWorks software. The design of microchannel heatsink rectangular microchannel heatsink. This is my dimension for microchannel heatsinks. Next, we go to meshing. Okay, for the meshing, we use relevant to 100 and use advanced size function to peroxistivity and concave. Relevant center used to find initial size heat, full assembly, smoothing height, transmission slow, span angle center find. For the body size, scoping method, geometry section, geometry we choose 2 body. For the definition, only change to element size 0.03. First photo is the after I finish the meshing, and the second photo is create name surface to input inlet, outlet, symmetry and heat source. Next, we go to CFD. For CFD, the boundary condition I change to reference frame to absolute. Velocity I insert 2 meter per second. Thermal temperature for for inlet nanofluid is 293. For heat source 160,000. For the solution control, the pressure is 0.3, the density is 1, body force is 1, momentum is 0.7, energy is 1. For the illustration, the number of lesions of this study is 1000. Next, we go to result and discussion. The first one is titanium, the velocity and temperature. The first one is 1 concentration. The middle one is 2 concentration percent, and lastly is 8 concentration percent. Same to zinc nanofluid for zincs. This is my temperature heat sink and the velocity of nanofluids. The nanofluid will initially be supplied at 2 meter per second to microchannel heatsinks. The result show is slowly increase around 3 meter per second. The temperature contour of microchannel heatsink was generated by using steady state thermal at the bottom of microchannel heatsink at 160,000 watt meter in heat flux. It showed the microchannel temperature slowly become cool and the nanofluid form cool, which in 293 Kelvin to the hot temperature around 300 Kelvin. This is my graph for velocity versus temperature. The figure show that the velocity flow versus temperature of microchannel heatsink by using nanofluid titanium water with different concentration. As the graph show, all nanofluids start at 2 meter per second velocity and 293 Kelvin for the temperature. The temperature at 1% concentration and at 297.11 Kelvin for 2 concentration and at 297.07 Kelvin, and lastly for at concentration and at 296.34 Kelvin. This show that one concentration is the higher temperature difference is better because it can absorb thermal conductivity of the wall and the bottom of microchannel heat sink. Okay, this is for zinc oxide velocity versus temperature. The figure show the velocity of flow versus temperature of microchannel heat sink by using nanofluid zinc oxide water with different concentration. As the graph show, all nanofluids start at 2 meter per second and 390 Kelvin for the temperature. The temperature at the first concentration and at 296.65 Kelvin for the second concentration and at 296.67 Kelvin, and lastly for at concentration and at 295.38 Kelvin. This shows that one concentration is a higher temperature difference is because it can absorb thermal conductivity of the wall and bottom of microchannel heat sink. Next we go to velocity vector. The result of velocity vector contour of microchannel heat sink was generated to show where the velocity flow happen in microchannel heat sink. Every side of the wall is slowly and only the middle of channel flow is higher, around 30 meter per second, because it less friction occur and there are no resistance. As you can see, for titanium oxide and zinc oxide nanofluid all almost the same, around 3 meter per second at the middle, and for the outside only slowly at 2 meter per second. Next we go to impact of nanofluid in titanium oxide water. The figure show the velocity flow versus heat transfer coefficient of microchannel heat sinks by using titanium oxide water with different concentration. As the graph show that all nanofluid start at 2 meter per second velocity and the heat transfer slowly increase when the velocity is increased. The heat transfer coefficient at 1% concentration and at 33,839.5 watt meter cube Kelvin for the second concentration and at 32,867.8 watt meter cube Kelvin, and lastly for the at concentration and at 26,174.13 watt meter cube Kelvin. This show that the 1% concentration higher heat transfer coefficient. The difference is because of the amount of heat transfer between nanofluid and solid surface by convection. The large of heat transfer coefficient is the more heat transfer occurs. Next we go to zinc oxide water. The figure show the velocity versus heat transfer coefficient of microchannel heat sink by using zinc oxide water with different concentration. A graph shows that all nanofluids start at 2 meter per second velocity and heat transfer slowly increase when the velocity is increased. The heat transfer coefficient at 1% concentration and at 33,147 watt meter cube Kelvin for the second concentration and at 32,607.37 watt meter cube Kelvin, and lastly for 8 concentration and at 24,894.74 watt meter cube Kelvin. This shows that 1% concentration is higher of heat transfer coefficient. Different is better because its amount of heat transfer between nanofluid and solid surface by convection. The larger the heat transfer coefficient, the more heat transfer occur. Next, we go to flow characteristic in nanofluid. From the figure show, the velocity of nanofluid almost the same when the center of the nanofluid slowly increase become around 3 meter per second from 2 meter per second. It also show nanofluid characteristic inside the microchannel heatsink. The nanofluid flow in category laminar flow because it don't have obstacle. There are two figure I put here. The first one is when the nanofluid come from the inlet, almost equal, and when the nanofluid travel into channel heat sinks, only the middle one become red because the velocity of nanofluid become 3 meter per second. Okay, next is velocity versus real number. The figure show why it is in laminar flow for nanofluid titanium oxide and zinc oxide water. The laminar flow range below 2300. The graph show that both nanofluid with different concentration are below 2300 for real number. As I can show the graph, the two graph of nanofluid, both are below 2300. Next, we go to comparison of nanofluid. This is the result for the outlet. The comparison for both nanofluid clearly show that titanium oxide is the best for the cooling method because the difference is 0.16 Kelvin in temperature and the velocity is the same. The small digit number can affect the performance of system. The first consideration only the best for in my simulation. For lastly is conclusion. By using ancient flow software, an analysis has been made to determine the impact of various nanofluid and analyze the effect of flow characteristic with various type of nanofluid. Based on the result, both nanofluid with different concentration have different outcome for velocity and temperature. They both have the same characteristics flow, laminar flow, because there is no obstacle in channel nanofluid. Comparison is being made between nanofluid titanium oxide and zinc oxide with different concentration. The best for cooling performance is titanium oxide. The temperature is 297.11 Kelvin because it can absorb the more thermal conductivity at the same velocity of 3.34 meter per second. The nanofluid for zinc oxide have the same velocity, but the temperature only 296.95 Kelvin. From the naked eyes, the difference is only a little in the cooling system, but it can affect on thermal. It can affect on performance in the system. Recommendation. The first one is fabric a new model and run the experiment study to compare the experimental study and simulation study. It can approve the simulation result correct or not. The second one is run the simulation with other type of nanofluid for titanium oxide and zinc oxide to find the which nanofluid is the best for cooling performance. And lastly is create a new design of microchannel heatsink and compare it with straight microchannel heatsink. Doing this can prove the straight microchannel heatsink is not necessary better than other microchannel heatsinks. Okay, this is my reference. Okay, that's all for me. Thank you.